Good afternoon and welcome to the I4Energy Citrus Research Exchange. My name is Therese Peffer. I'm the Associate Director of I4Energy. We'd like to welcome those in the room here as well as those on the other UC campuses at Merced, Davis, and at UC Santa Cruz. I just want to bring to your attention that the next I4Energy Research Exchange will be November 22nd. That's a week from Friday. And the speaker will be Marianne Payette from Lawrence Berkeley National Lab, and she'll be talking about automating demand response. And then 3 weeks from today, on a Wednesday, December 4th, that will be Michael Isaacson from UC Santa Cruz, and talking about community-scale renewable energy microgrids. So with that, I'll introduce today's speaker. Duncan Callaway joined the Energy and Resources Group as assistant professor in the fall of 2009, and he also holds a courtesy appointment in the Department of Mechanical Engineering here at UC Berkeley. His research can be categorized into three areas: modeling and control of aggregated storage devices, power management, and systems analysis of energy technologies and their impact. His research involves the use of a variety of methods, including stochastic modeling, system identification, dynamics and control, and spatial analysis. In general, his work focuses on improving energy efficiency and renewable resource utilization through novel energy system configuration and control strategies. Some of the specific application areas he works on includes wind energy, demand response and load control, and plug-in electric vehicles. So please join me in welcoming Professor Callaway.
Great. Thank you, Therese. It's a pleasure to be here. Thanks to everybody for coming. It's great to see you all in the audience. As Therese mentioned, I'll be speaking today about some work that my students and I are doing on demand-side modeling. I'm also actually going to begin the talk by talking about some work that we've been doing to quantify the impact that variable renewables have on power system operations. So this is work that's done with the support of the California Public Utility Commission and the Department of Energy's Future Grid Initiative. And the students that have contributed to this, done all of the enormously heavy lifting, have been Mark Dyson, Johanna Matthew, and Michelangelo Tabone. Okay, so let me just go ahead and start by setting the scene. The solar scene, I think, is particularly interesting when we think about variable renewables and what's happening these days, because there's just been extraordinary growth, not only there's been growth in capacity of installed photovoltaics, but there's also been extraordinary declines in the cost of photovoltaics. And there's, that cost decline, which is just, at least you can see the trend depicted on this figure, it may stop tomorrow. I can't predict the future, but all indications are that, it's pretty tempting to just keep drawing a line going down, costs dropping. And, I think it's reasonable to think that we'll get to $1 a watt in the near term. And this is $1 a watt on rooftops, potentially. So it's an extraordinary opportunity, I think, for renewable energy. So every indication is that we're going to be getting a lot more photovoltaics on the grid. And if you think also just about what California's own goals are, we have by 2020 a target of having 12 gigawatts of distributed generation, and that's mostly going to be solar, or we expect it will be. But as I'm sure that you all are aware, wind and solar are variable producers of electricity. And so let's first start by looking on this figure, which shows on the y-axis something that represents the generation from either one PV site or an aggregation of sites, and on the x-axis it's the time of production. So if you let's start by looking at the red line, and you can see this is 1 minute production data, and you can see that there's a ton of volatility in that time series. And your initial concern might be, well, if we have to balance that variability on the supply side using combustion turbines or something like that, what will the system-wide impacts be? Is that going to be just completely unmanageable? But if you start to look at what happens when you average over spatial scales, you can see that the black line is averaging 15 sites within a 5-kilometer radius. And you can see in that case, we start to get some attenuation of that variability. So the question that we wanted to really directly address in this research that I'm going to describe to you is how do we quantify that attenuation of variability as you aggregate across larger spatial scales? Or more specifically, if we think about different configurations of distributed renewables over spatial scales, what do the different outcomes look like in terms of the total variability on the system? So, of course, in this case, there's several kinds of variability. Some of it is just coming from the solar diurnal cycle. Some of it, on the other hand, is coming from PV array orientation, potentially in combination with shading on PV arrays that might come just from rooftops or trees nearby. But then, of course, the majority of this is happening due to cloud transients. And so what we had to make a big effort in the research that I'll describe to you today in doing is to describe how those cloud transients affect variability. Okay, so that's just some motivation about what we'll be doing today, and I see that my slides are getting cut off, unfortunately. Not on any of these screens here, but it is cut off on the projector, so you're going to have to just take my word for some of what's on here, particularly at the bottom. So variability and uncertainty, of course, have to be balanced on power systems. And recent studies in California that precede what I'm going to talk to you about today suggest that we need as much as 4 gigawatts of new flexible capacity by 2020 to achieve what we call a 33% renewable portfolio standard. I want to be clear that that's capacity not to serve peak demand, but just to provide flexibility. And that's quite a lot of generation. So in part one of the talk, we're going to go into this analysis of solar variability that I talked about on the previous slide. And specifically, can we quantify just for distributed photovoltaics, not for wind, but just for distributed photovoltaics, how much flexible generation capacity do we need by 2020? So then in the second talk, I'm going to go pretty quickly through a possible solution, a way to provide that flexibility with the demand side instead of the supply side. So instead of using combustion turbines to ramp up and down, can we use electricity loads to balance the fluctuation, most importantly, that short timescale fluctuation? So I think what's compelling about this research area, and I've been working in it for a few years now, is that the infrastructure in some senses is there already. Certainly the loads are already there. And it's really just a matter of getting communication, modeling, and control down right so that we can actually coordinate those loads to get some sort of aggregate response that we want. Okay, so let's go ahead and just, I'll start talking about specifically about the operational impacts work. And I'm going to do that with this somewhat nasty figure from the California ISO. But what I want you to get away from this figure is how system operators think about balancing variability and uncertainty. So one thing that I should say from the outset is that variability and uncertainty in demand has been there for over a century now. And system operators have had to think about changing the output of generators to deal with the fact that how we consume electricity varies over a day and over seasons, but also to account for the fact that they can't predict exactly what consumption of electricity will be at any point in time. So it looks like maybe we'll get some... look at that. Perfect. Okay, you don't have to take my word for what's on the slides anymore. Thank you. Okay, but putting renewables on the grid presents much more significant challenges with respect to that variability and uncertainty. So, but let's just to start to frame you, to give you a point of reference on this figure, start by looking at the green line. So what we're looking at is something that's like megawatts of total demand on the grid. And we could also think of this as net demand. That is demand for electricity minus what variable renewables are doing. So the way that you think about the green line is for all of the generators that we can dispatch, like combustion turbines or hydro plants, what do they have to do in aggregate? So the green line would be what they ultimately have to do. Now, when the system operator is thinking about things day ahead, they don't know exactly what that green line is going to be, but they can do an okay job of thinking, well, over an hour, on average, what is it going to be? And that's what this red line represents. So that's like something like the system operator's best estimate day ahead or hour ahead of what that green line is going to be. And they coordinate generation to be ready to produce that amount. But then as they approach the actual moment of demand or net demand, if they're approximately 10 minutes away, they can get a better estimate of what's going to happen in a 5-minute interval. And that's what these step lines are meant to represent. Those are average net demand over a 5-minute interval. So those are forecasted something on the order of 10 minutes in advance. And then generation is redispatched. That is, they try to economically coordinate generation to follow this blue step line. But then, of course, there's still some amount of variability and uncertainty that can't be managed before that actual moment of operation. So what this green line represents, the difference, rather, between the blue and the green line, is the amount of megawatts of production that generators have to provide in real time. And so these generators are basically responding to system frequency. So for that reason, we call this difference between the blue and the red regulation or frequency regulation. I'm going to refer to it either as regulation or automatic generation control throughout the talk. It's actually an automated control loop that's centralized that governs all of the generators within a particular balancing area. So the difference between the red line and the blue line is typically referred to as load following. So this is a longer time scale, often larger deviations from the red line to the blue line. So now to sort of bring you back to what we're going to be talking about for the rest of at least the first half of the talk, what I want to be able to do is quantify the impact that distributed photovoltaics will have on that difference between the red and the blue. That is, how much load following capacity do we need? And how much additional frequency regulation capacity do we need? So this is actually something that's a little bit unique in the way that we're approaching the problem. So people have thought about the variability of distributed photovoltaics before, but not specifically in the context of what the system operator impacts are. So we're trying to couch this as much as possible in real sort of relevant planning metrics. Okay, so that's actually the first part of this slide here that I just said, that we're trying to focus on operational impacts. That is load following and frequency regulation requirements. Something else that's been really powerful, I think, in this analysis is that we're working with real distributed photovoltaic data rather than either just solar measurements of incoming solar radiation or estimates from other sorts of weather stations. So in this case, we're working with a photovoltaic integrator that has over 7,000 customer sites, mostly in the West. We're going to be focusing just on the sites that they have in California. And we can say, well, what is the actual production from a PV system either every 15 minutes or every 1 minute? And the advantage of working with the real data is that it captures the impact of the PV orientation, any actual shading that's present at that site. If the equipment fails, that's in our data. So we can actually quantify, to some extent, variability that can't be quantified using other kinds of measurements. The analysis is going to focus on both very small spatial scales, and we use that primarily to get at that spatial averaging that I was talking about. But we'll also, by the end of this first part of the talk about very large spatial scales. So essentially, what are the operational impacts on the state of California? So let me just talk a little bit more about the data set then. So on the small spatial scales, we've got instantaneous voltage and current from small, mostly residential installations once per minute. And we have a certain number in various parts of the state of California over some period of time. And our objective will be to build models for these periods of time in these locations. And then we use those models to extrapolate out to larger areas. So these areas we sampled are roughly 256 square kilometers. And we chose that area because it's approximately equal to something we call a subload aggregation point in the state of California. And that's one way of thinking about the smallest unit that system operators care about, the smallest sort of spatial area that system operators care about. So then we take the production from an individual system and decompose it into individual pieces. So this plot here might look pretty similar to that plot that I showed you a couple of slides ago that talks about how system operators think about variability and uncertainty. So what we did is we took for one individual PV system, we produced a time series that looks like its average over an hour. And one thing I didn't say before is that there are 20-minute ramps in between. That is, if the hour ends sort of right here in the middle of that ramp, there's 10 minutes on one side and 10 minutes on the other of ramping between the averages. And system operators think about that for net demand as well. So we construct the average of the actual signal, and then what the black line represents, the points of the black line at least, are the 5-minute averages of the signal. And then the blue dots are the actual signal itself, the actual measurements. So the difference then between these lines, as I was saying before, represent for an individual system its contribution to load following or frequency regulation or automatic generation control and frequency regulation. They're interchangeable terms. So these are those differences. And that's for one individual site. So one thing that I should say as a caveat right now that you may be thinking is that we're taking the average of the actual time series, and when we bake that into system impacts, we're basically making an implicit assumption that the system operator can perfectly forecast the average, which is obviously not the correct assumption. But the reason that we did this is that we wanted first to get a sense of what the just the solar resource alone, how it contributes to system-wide variability. And then a next step that I'll very briefly mention would be to build a forecast error model into our model. But we didn't, as a first step, want to have to make any predictions about what those forecast error models would look like. So the basic approach then is to parameterize the probability distributions of differences. That is, if we think about the difference between the black and the blue or the red and the black, we get a distribution of differences, and we want to characterize that probability distribution. And the reason that we want to do that is to predict, well, what are the tails of that distribution look like? And that gives us a recommendation to the California Independent System Operator, for example, for how much load following or automatic generation control capacity they'll need in the future, because they typically plan for extreme events. So the hard part is that the distributions are quite complicated, as you might imagine. So there's no parametric probability distribution that we can just plop down on the time series itself. The sites themselves are also spatially autocorrelated, as I suggested a little while ago. So if it's cloudy here, it tends to be cloudy over here, but it's a little bit less likely to be cloudy over here and even less likely to be cloudy over here. And we wanted to be able to capture that spatial autocorrelation in the data. So the really hard part is that we want to characterize the extremes of the distribution. So it would be one thing if we were happy to get the average and the standard deviation. But we're talking about going way, way out into very low probability events. So as we started looking at the data, one of the things that we noticed is that production from individual sites tends to sort of happen, the volatility looks like it occurs kind of in categories, right? So this is actually typical for Berkeley, right, where there's a morning cloud period. So the green line is what would be produced if there were no clouds at all. So there's like a morning cloudy period, kind of transitional time, and then partly cloudy as you're approaching noon, and then a nice sunny afternoon. And you can see that it appears that there are just different regimes of volatility in these periods. And so what we took as sort of a hypothesis is that, well, if we can basically classify each period into different categories and then fit distributions to those different periods, maybe we would get a nice representation of those distributions. So what this down here shows you is what happens if we just kind of eyeball what's happening. So this is just sort of basically rule of thumb we use to figure out, well, when is it cloudy, partly cloudy, or sunny? But what we wanted to do with the model, and this is Michelangelo Tibone, his work that I'm talking about now, and it was his idea to say, well, why don't we estimate endogenously to the model estimation process the probability of being in one of these particular states. Now, we're not actually going to say it is definitely cloudy, it is definitely partly cloudy, but instead we're just going to have discrete states that we allow the model to assign to the current moment in time. So the way that we do that is with a hidden state Markov model. And so the idea is that at each point in time, there's some volatility state that we don't know. We're going to index that. We're going to call it V and index it by 1, 2, 3, and so on to represent time. So there's some volatility state that we don't know, but if we, given that volatility state, then we'll say there is a distribution, a probability distribution of outputs that's possible. And the actual production that occurs at a given point in time is our observation Y, or rather the difference between those hourly or 5-minute averages is our observation Y. And then we'll also allow the model to have some exogenous inputs, and I'll talk a little bit about what these might be in just a second. But these basically will give us an ability to affect the state transition probabilities between volatility states. So it's a Markov model in the sense that volatility states have a transition probability. We can go with some probability from here to here. We'll go from state 1 to state 2. Another probability will go to state 1 to state 3, and so on. These exogenous inputs will basically modify that transition probability matrix such that we can hopefully capture a little bit more accurately the variability on different scales. Okay, what should those exogenous inputs be? Now, I talked about this short timescale data, the 1-minute data, but we also wanted to leverage the fact that we've got across the entire state of California, we've got a very nice set of 15-minute data. So this is 15-minute production from these mostly residential systems. And the basic idea, and I don't want to wade too far into this just in the interest of time, but the basic idea is to use those observations to categorize them into discrete states and to use those categories of observations to inform what the state transition probability matrix ought to be in the Markov model. And the reason that we want to do that is largely because when we take these small spatial scale models and try to extrapolate to the entire state of California what we think variability impacts would be, we can take our 15-minute data and use that as inputs into a simulation model to figure out statewide impacts. So the basic model looks like this. So we'll say there's a variable or a vector, y sub CL is the clear sky. That is what the production or the volatility, not the volatility, but the difference between, for example, 1 hour and 5-minute or 5-minute and instantaneous measurements if there were no clouds in the sky. That's what this vector represents. And then we'll make an assumption that our model looks like this. It's a multivariate Gaussian. Each individual observation from each site, and an observation is a difference between 5-minute and actual or 1 hour and 5-minute averages. Each observation is distributed like a multivariate Gaussian with average equal to the clear sky. And then this giant variance-covariance matrix. And the things that, so it's a covariance matrix, and that allows us to say that the production between adjacent sites can be correlated. And the things that determine the structure of that covariance matrix are the volatility state. That is, for each individual site, you can intuitively think, is it partly cloudy, is it sunny? And then a vector of parameters phi that describe the spatial autocorrelation. And so that's this function that we're going to use to describe the spatial autocorrelation is down here. It's just a simple exponential decay. So to recap, that variance-covariance matrix is a function of the volatility state, and that largely drives what the variance is at an individual site. And then this set of parameters phi describe an exponential decay that describe the covariance between sites, so the off-diagonals of that variance-covariance matrix. So the way that the model gets estimated is that the first step is to estimate endogenously to the model what's the volatility state, what's the variance, and then what's a state transition probability matrix that is going from one volatility state to another as you march forward in time. And that's going to be a function of our exogenous inputs, which is coming from the 15-minute data. And then we estimate one model for each of those 256 square kilometer regions. And we estimate that with a straightforward algorithm called expectation maximization. And that spits out state transition matrix, and volatility, which are the key things that we care about. And then we post-process the results to figure out what the what the spatial autocorrelation function ought to look like. But we condition that spatial autocorrelation function on which volatility states each individual system are in. So on this figure, I just want to have you look at the left plot to give you an idea of how we decided how many states we should have. So there's actually a modeling decision we had to make was, well, should there be 3 volatility states, 4, 5, 6, 7? And so if you look at the log likelihood of the model, what we're plotting here on the y-axis is the percent increase from going from, for example, from a 2-state model to a 3-state model in the log likelihood. So this is the improvement that we got by choosing a 3-state model over a 2-state model. This is the improvement we got by choosing a 4, by choosing a 5, and then this is the improvement we got by choosing a 6-state model. So we said, well, it looks like 5 is kind of the point where we're still getting improvement, and so for the sake of parsimony, we're going to just stop at 5. We're going to say that 5 states is a good number to estimate. This is one way of validating, that we chose to validate the model. And these are called QQ plots, quantile plots. And the way to think about it is on each axis, I'm showing you something like the number of standard deviations from the mean of the distribution. And the way that you think about this point is that this point represents on the x-axis the number of standard deviations away that the most extreme point is that we model. If we simulate the model, just choose a bunch of random variables from the model, this would be the most extreme point in the negative direction. If we actually look at the data that we use to fit that model, this is also on the y-axis, that's the most extreme point. So you can see that to the extent these, and then each one of these points is just a ranking. So somewhere in here is the 100th most extreme point on both distributions. And so this is a ranking, and to the extent they lie on the y equals x line, we're happy. That means that the distributions look basically the same. So you can see, in this case, what I'm showing you is the simulated distribution from our model versus the data that we used to fit it. We actually withheld 25% of the data to do additional validation, and so what this is showing you is the QQ plot for the simulated distribution versus that 25% of data that we withheld. So again, you can see that it pretty nicely lies on the line y equals x. So when you just look at those left figures, we're happy, right? Because it looks like the model's performing well. What I'm going to show you over here is this actually, we're not going to go much into detail into using these, but I'll just at least give you a sense of what these QQ plots tell us. So we also made some assumptions, and I'm going to try not to wade too far into this because I want to get through some other things, but I just want to describe it. We made some assumptions about the correlation between volatility states, the hidden states in the system, basically to try to manipulate the output of the model to either give us an upper bound or a lower bound on the volatility so that we could try to characterize in simulations, well, this is still an estimation of the extreme points, so can we characterize an upper bound and a lower bound? And so what this is telling us is for one particular set of assumptions about the volatility states, we're getting 5 standard deviations away for the actual data, but only 4 or so standard deviations away for the simulated data. So that's suggesting that we're getting a lower bound. And then on this case, it's the opposite. We're getting sort of an upper bound. So I'm not going to go into those modeling details too far, but you at least get a sense of how we think about trying to characterize how well the model is performing. So the basic approach then to extrapolating this model out to the whole state to understand what kind of balancing capacity we need in the future is to divide the state into regions where we've got 15-minute data, and we divide it into 2-kilometer square cells. And this, it turns out, there's sort of testimony to the power of the data set, that covers about 40% of California's population. So if we divide the state into 4 square kilometer cells, and say for all those cells, where do we actually have 15-minute data? Those cells cover 40% of the state, of the state's population. And then we use the 15-minute data point closest to the centroid of each cell as our exogenous inputs. And we simulate the hidden Markov model with those 15-minute data. And then we look at 3 different PV arrangements. First, a distributed one where we assume that in each cell, the PV systems are randomly distributed throughout the cell. And that would be like, that's an approximation of if we had rooftop solar on residential buildings. Then we look at what we call a community scenario, which is what would happen if all of the PV, same capacity of PV in each cell as in the distributed scenario, but it's all concentrated at one little square in the middle of the cell. So what that's basically doing is saying we're not going to, within a 2 kilometer by 2 kilometer cell, we're not going to allow there to be virtually any spatial averaging to go on, right? There's going to be strong spatial autocorrelation for the production in that one site. And then we also looked at a centralized scenario, which is we looked at an NREL resource map. We said, where is the solar resource the best in the state and of all the places where we have the 15-minute data? And we chose those. And we just like piled all of the PV into those one regions. So this is basically the Mojave Desert scenario, right? This is like, what if we put all the PV in one place for the sake of basically efficiency? We're going to get much better capacity factors in that centralized scenario. But as you might imagine, because of that spatial autocorrelation, we're going to get higher requirements on balancing capacity. And so one of the things that's fun that we can do with this model is we can actually quantify what is the penalty to go from a highly distributed scenario to a highly centralized scenario. And then in this case, we made predictions for AGC, frequency regulation, and load following, assuming we got to California's 12 gigawatt target. And so this shows the results. And before you go, so let's first start by just looking at the first 3 bars. Okay, so try if you can to block out the other 6 bars for the moment. So what we're looking at is for the distributed, community, and centralized scenario, how much balancing capacity do we need? What's the sum of the requirement for frequency regulation and load following? And we can show that in terms of total gigawatts, and we can show that in terms of the percentage of the installed PV capacity. So as you might expect, we go from distributed having only a requirement of about 7%, which is roughly 1 gigawatt, a little bit less than 1 gigawatt of balancing capacity, up to basically double that if we go to the centralized scenario. So this, just to put it into context, a couple of things. One is that I suggested to you that there's an estimation that we need 4 gigawatts of balancing capacity to deal with the state's entire renewable portfolio standard. But this 12 gigawatt requirement of distributed PV would only meet a fraction of that renewable portfolio standard. I should know it off the top of my head, but it's on the order of like 25% of the total renewable portfolio standard that we have. So what this is saying is that distributed PV, although it appears to be a good solution relative to centralized, it still might certainly centralized might require a larger amount of balancing capacity than system operators are currently projecting. Another way to think about it is that the National Renewable Energy Lab has a rule that says that 5% of the capacity actually 5% of what's forecasted for production from renewables is how much you should be committing for reserves in real time. But we see in the best case we're getting 7% of the total installed capacity. So I think that this suggests that rule of thumb, the 5%, is probably quite a bit too low. The next interesting thing to look at then is let's look in sort of clusters of 3. So this is our first cluster of 3, second cluster of 3, and third. So in the first cluster I was talking to you about, I was assuming that you do all of that balancing at the level of the state. That is, that we're basically pooling together production from all of those PV systems and then saying how much variability is left to deal with. So at the county level balancing scenario, we said, well, what if we actually decided to do the balancing at the level of a spatial area that is a county? Now, counties aren't relevant to system operators, but it's what the GIS software gives us easily. And it's something that's sort of, it's approximate to what a subload aggregation point might look like in the system. And you can see that there's basically something like a doubling in the requirement. And then we also said, well, what if we actually balanced within each 4 square kilometers? So we had an ability either with storage or distributed generation to perfectly balance out that variability within each 4 kilometer square block. And you can see that there's an enormous impact in terms of how much is required. So I actually think that the most interesting comparison is between the state level and the 4 kilometer balancing area. And the reason is because there are, I think, for some ways of thinking about it, legitimate reasons to imagine that we should do our balancing like at the level of a home. So to the extent you've got PV variability, what if you've also got storage behind the meter? Should we use that storage to balance out the variability there? Or should we use demand response to balance out the variability? And what this is saying is that, well, there may be other reasons to do it, but it's not, you shouldn't cite as a reason that you can use less capacity. For sure you need like an order of magnitude, potentially more capacity than you need if you balance at the level of the state. Okay, so just some important caveats. So I've talked a little bit about this interpretation. So one thing that I did mention is that we're not dealing with forecast error, and so this would only tend to increase the estimates for how much capacity is required. But it's going to be conditional on whatever we assume the forecast error model is. So this is something that's actually in progress right now. Second thing, it's actually the first bullet, is that some of you may have picked up on this. We're only looking at requirements for photovoltaics, but what the system operator really cares about is the sum of requirements for PV and wind and load. And we need to stick all of those things together in a model. And that's another thing that's in progress. And then the third thing is that right now we're focusing on extrema over relatively long timescales. And so that it's useful for forecasting how much extra capacity we might need to build in the future. But I think there's reason to think that we could use this as like a day-ahead forecasting tool for reserves. And that would, be, I think, be another interesting step. So instead of how much do we build in 10 years, how much do we commit tomorrow? Okay, so in the second part of the talk, I want to just talk about a potential solution to balancing this variability. So I've talked a lot about the first one already. So to the extent we've got variability from wind and solar, we could dispatch conventional generators, just move them up and down in response to the wind and solar. Disadvantages, so advantage to doing that is that that's what we do today. And the system, to the extent, as long as we can get enough capacity online, it ought to be a relatively straightforward solution. Disadvantages, it requires those generators to be running, but always at part load. That is, they have to have some ability to move up to increase their production if there's a reduction in PV or wind. So inefficient at part load and more generators running all at part load. So it's an efficiency penalty on the system. Second thing is that because of that inefficiency, their heat, another way to think about that is it's a poor heat rate and a degradation in CO2 emissions and economics. So another solution, and in fact, this is one that's being pursued, at least in a very sort of coarse way, is to use storage to manage the problem. So some of you may have seen that the CPUC, actually under the leadership of graduate Carlo Peterman, just approved a mandate to the investor-owned utilities to procure about 2 gigawatts of storage by 2020. With largely for the reason, justification is largely that you can use it for balancing renewables. But I think that most people would agree that at least today the economics of storage are very challenging to make a case for. And there's a round-trip efficiency penalty that degrades the economics even further. So it may be that sometime in the future storage really is going to be the solution. But I think for this kind of variability, short timescale variability, and any time in the near term, I'm less optimistic about that solution. So the third thing that we've been focusing on in our research is to coordinate the demand side to balance that variability. And I'll talk about that in the rest of the talk. So basically what I'm saying is that we, instead of moving generators around or storage around, if there's an increase in solar production, we increase demand just a little bit to deal with that. And if there's a reduction in solar, we reduce demand a little bit. And on short time scales, with thermostatically controlled loads, that's a I think, quite a workable solution because we have thermal inertia in those loads, and to the extent you're changing when an air conditioner operates from one 5-minute interval to another, there's basically an imperceptible impact on the customer, right? So, but one major problem with that, or the problem that we've been trying to solve in the research, comes from requirements that system operators have. So this is a system operator's control room, and this one is in Folsom, the California ISO's control room. And they are accustomed to extraordinary visibility into what resources in the system are doing. That is, they've got high precision telemetry on every single resource that's moving around in real time. And so this is what's called a remote terminal unit. This is a piece of the energy management system that system operators expect to be on every single generator. And this little box ties into the EMS and brings real-time 4-second information back to the system operator. So there's a study done in Southern California Edison that suggested to not just to buy this box, but basically to build the infrastructure to integrate into the EMS was going to cost on the order of $70,000 for individual loads, which is, if we're talking about small loads in particular, is totally untenable. And so what we've been thinking about is an alternative scenario where instead of measuring at individual loads, we take measurements at the level of distribution substations. And we use that as the point where we're feeding information back to the system operator. So why do that? One reason is that, well, it's only 1 meter instead of 1,000 meters on a distribution feeder, for example. But another is that actually that meter in many cases is already there because load-serving entities, the investor-owned utilities, often have that SCADA equipment in their substations already. So what we thought about was, well, what if we take measurements here and then use that basically as information to infer the state of the individual loads with, where these would be loads that are thermostatically controlled going through a hysteresis loop like this, where if it's a heater, for example, the temperature would go down for some period of time while it's off, and then it would come on, it would go back on again for some period of time. It just goes through that loop. So we're thinking specifically about loads that execute this kind of a control loop. So the idea is that if you get some signal, either from a market or from the energy management system, from the system operator, you want to turn this into something that looks like that. And so the idea is that you estimate the states of the loads, you put those state estimates into some sort of central controller, broadcast information back out to the loads, and hopefully get something in terms of aggregate consumption that looks like this. So I'll talk in a little bit more detail about how this control might work and on the next slide, but I just want to say one more thing about why we're pursuing this particular framework. And the one reason is that the SCADA equipment is there. Another reason is that smart meters, advanced metering infrastructure, are very good at listening to information. As some of you may know, they're terrible at quickly, at least, sending information up to some sort of central place. But they're, in some cases at least, very good at receiving broadcasted information. So this is a mechanism that we could use where we've already got smart meters, we've already got distribution substation SCADA. We really just have to broadcast information and then have some local control infrastructure. So it's potentially the least cost, at least in terms of infrastructure, way of getting to some sort of a workable demand response scenario. Let me just skip ahead to discuss what the model looks like. So this is the model we've been working with, where the idea is that we take, so the way to think about what's on the x-axis is this is what we call normalized temperature. So imagine that this is the temperature deadband for every load, and it goes normalized between 0 and 1. So 0 is the coldest, 1 is the warmest. And instead of describing the temperature state of individual loads, we describe how many loads are in each discrete bin of temperature. And that becomes the state. So the x vector in this model is the fraction of thermostatically controlled loads in each bin. And then if you look just at this first bit of the model, we're saying that given the state of, or the distribution of loads across those bins of vector x at time k, A tells us how we transition to a new distribution at time k plus 1. So this is just a simple linear time invariant model. We've looked at other formulations where it's not time invariant, but in this case what I'm showing you is just time invariant. But then there's also, and then we also say, well, we know an aggregate power from this collection of loads. That's our observation y. And so this C matrix is basically what we call an observer matrix, and it takes the actual state of the system and maps it to our observations. Yeah, question? I mean the actual temperature. So the idea would be that a set point, so most thermostats operate with something like a 0.5 degree Celsius deadband. And so this would be the temperature within that 0.5 degree Celsius deadband. So it's a relatively small distribution of temperatures. So then the way the control works is that we could broadcast a signal out to the loads that say, if your state is such that you were about to switch a little early to the on state. And this would give us an increase in consumption on the system. Or if your state was such that you were getting ready to turn off, but you haven't yet, turn off a little bit early, and that gives us a reduction in power consumption on the system. So the opportunities that with this model formulation is that it's simple to model a variety of control signals. We can get our state estimates from Kalman filtering. We can even get parameter estimates from a nonlinear filter. And we can apply a wide array of control tools. So others have worked with similar formulations using, there's actually a nonlinear formulation for which sliding mode makes sense. We've worked a little bit with MPC formulations, and others have used just LQR. So there's a lot of, it's a very general modeling formulation that we can apply a lot of control theoretic tools to. So let me actually just jump to talking about some results. So we looked at a case where we wanted to understand, well, what are the returns to more information, or rather, what's the penalty to having less information? And so we looked at a reference case. This is all simulations, and we're trying to get some pilots going, but it's slow going. But we looked at a reference case where we assumed we know everything, basically temperature at all the loads, power at all the loads, and then we asked those loads to follow something that looks like a load following signal. And in that case, in simulation, we get a 6% RMS error. So that's quite good. And then let me just jump ahead to this extreme case 2, where we meter only the aggregate power at the distribution substation, and we infer states using a Kalman filter. And in that case, we get 5% RMS error. And this is something that's at least comparable to how typical generators perform. So it looks like maybe a lot of RMS error, but it's at least... from what we can tell, it's comparable with industry practice. We also did some other work to try to quantify the size of the resource using, that is, how many gigawatts of demand response can we get with this kind of strategy. One thing that I should have been clear about is that because the control is just happening within this deadband, in principle, there's no impact on the consumer, right? Because this is the range of temperatures that the consumer would have experienced otherwise. We're just switching loads slightly early or ahead of when they would have switched otherwise. And so then we said, well, given what we know about load penetration and climate in the state of California, what kind of resource potential is there? So we looked at air conditioners, heat pumps, water heaters, and refrigerators, and found that in that case, we've got, just with residential loads, 2 Three Gorges dams of power capacity. That's 40 gigawatts of capacity at the point in time when there's the largest amount of capacity. One thing you might be thinking, though, is that air conditioners are on only for a fraction of the year. And so this resource size obviously gets smaller when it's cool out, right? And then if you think about it as a battery, it's 10 gigawatt hours of energy storage. So that is, we can do 40 gigawatts for roughly 15 minutes. And then these are just some numbers that look at, with a few different ways of estimating what the value is, how much you might be able to pay one individual owner of these loads for providing either regulation, load following, or I'm not going to talk about the energy arbitrage really, but if we just focus on these two, regulation and load following, you can see that for some loads, at least, we're talking about a few $100s a year for at least the very fast timescale stuff. For the load following, though, there's not a lot of value there. So one natural question then is, would you do it if it's only $10 or $30 a year? And one answer might be if the program directly offsets renewable generation, maybe that encourages more participation. And in fact, you might get more participation if you don't pay anything and just say you're offsetting PV rather than pay something and you're offsetting PV. We're also looking at options where the payout might be probabilistic. That is, you get credits to play in a lottery and you get paid $10,000 with probability 1 in 10,000 instead of $1 all the time. So just a few concluding remarks. For solar variability, we find that conditioning on solar output distributions on discrete volatility states gives us really nice Gaussian distributions. And this allows us to get to a point where we say the configuration and the balancing strategy to distributed photovoltaics greatly impacts the scale of the problem. And then on the demand-side flexibility side, we see that there are potentially very low-cost communication strategies, very big resource, but there's a lot of work still to be done here to be sure on the validation and modeling side of things. And with that, I'll conclude with only a minute for questions, but thank you.
And Duncan did say he could stay after for a few minutes if there are other questions.
Yeah.
But do we have a burning question now?
In your modeling of the solar variability resource, it looked like your data was just down to 1 minute time scale.
Yeah.
Is it important to take into account some of the faster control loops that are happening, like the droop control on generators and things like that?
Yes, this is a good question. And so let's actually just talk about, for a second, automatic generation control. That frequency regulation that I've been talking about nominally is executed on 4-second time steps, right? So at least the signals that are getting distributed are once every 4 seconds. There's an update to what that load or the frequency regulation requirement is. So one major comment, I think, so ideally we'd have better data. We'd have faster timescale data to characterize on the sub-minute timescale what's going on. But we do see that if we just look at the 1 minute timescale, that the autocorrelation across spatial scales drops off really fast, even at 1 minute. And so there's every reason to think that going to shorter timescales is going to drop off even faster. So what that means is that to the extent there's variability at one site here, it's not inversely correlated, but at least it's not correlated with variability elsewhere. And so the result is a requirement that's relatively low. So we saw actually, I don't know if I have the figure here, but there's a way to look at things. I don't have it. If you look at those bar charts that I was showing you with the final results, the fraction of it, of the total reserve requirement that comes from frequency regulation is really small. It's mostly load following. And so I don't think that we're going to need much. I think that it's a blind spot that we don't have the 5-star timescale data, but I don't think we're missing much at all. Yeah.
I think we'd like to close
okay.
and let people, if you have individual questions, just come up and ask Duncan. So thank you again, Duncan.
Okay, thanks for coming.